I wanted to be sure to include a short discussion about what people call solving triangles. We're going to have a sort of generic setup for our triangles. I'll draw the bottom as though it's horizontal. I'll call the angles at the bottom A and B. I'll call the angle at the top capital C, and little a, little b, and little c are the distances along the sides opposite one of the angles. So little a is the length of the side opposite angle capital A. If you look at the side opposite angle capital B, we're going to call that little b. The distance along the side opposite angle capital C is little c. In the name of brevity, I'm just going to state the law of sines. This is not very hard to show, but I'm just going to omit that part. If you take an angle and the length of the side opposite that angle, if you calculate the sine of the angle divided by the length of the other angle, it turns out it doesn't matter which angle side pair you're looking at. So sine A over little a is the same as sine B over little b, which is the same as sine of C over little c. Or, since all three of these numbers are equal, their reciprocals are equal as well. So these three numbers are all the same. This statement is called the law of sines, and in some circumstances, it will allow us to solve triangles. As an example, let's think about this triangle. We know up front that angle A is 47 degrees and angle B is 53 degrees. We also know that distance little c is 10 units and distance little a is 20. And I want to solve the triangle. I want to figure out all the things that I don't know, which in this case is very limited. The only thing that I don't know is the length of side little b and the measure of angle C. One thing about triangles is the angles have to add up to be 180 degrees. So 47 degrees plus 53 degrees plus this other angle has to add up to be 180 degrees. If you subtract 47 and 53 from both sides, you find out that angle capital C is actually 80 degrees. So this angle is known to us now. Among other things, the law of sine says that distance little b over sine of angle B is distance little a over sine of angle A, and we know what b and little a and capital A are, so I can write this equality. If you multiply both sides by sine of 53 degrees, you get this formula. Now my angles are in degrees, and I'm expressing things in terms of trig functions of the angles. So make sure your calculator is set in degree mode. Calculate 20 divided by 47. Don't forget to close parentheses. And then multiply by sine of 53 degrees. And you'll find out that the one remaining piece of information that we don't know is that distance little b is about 21.8399. Of course, the reason that previous example was pretty easy was I knew two of the angles, which means figuring the third one out was basically for free. What if you have this situation? You know that angle capital A is 39 degrees. You know the length of the side opposite angle capital A is 20. You know the length of side little b, which is opposite angle capital B, is 10, but that's all you know. Unlike the previous example, I can't immediately tell you what all the angles are, but I do know this. I know an angle and the length of the side opposite that angle. So I know a pair of numbers that figures into the law of sines. I also know the size of little b, the distance along that edge, is 10. So part of the law of sines says sine of b over little b is sine of a over little a. I know what little b is, it's 10. I know that a is 39 degrees, and I know that little a is 20. So if you do the multiplications, you find out that sine of b is 0.3146601. In a triangle, we're always going to take the angles to be between 0 and 180 degrees, and distances, of course, can't be negative. So if this had come up and said that sine of b was 1.3 or something like that, that's impossible because sine never gets bigger than 1. If that had happened and I'd done my work correctly, that would tell me there's no triangle that goes with the given data that I'm putting in. But that's not what happened here. Sine of b is about 0.314. We've got a problem though. In a triangle, two of the angles could be very small, very close to 0. That would make the other angle close to 180 degrees. So I have to think, when thinking about triangles, about all angles between 0 and 180 degrees. And unfortunately, there's two of these angles that make sine of b equal to 0.31466 some odd. I'm going to make a short discussion about inverse trig functions in a while, but for now I'm just going to be mercenary and we'll use our calculator methods on this. Keep in mind, our angles are in degrees, so you have to make sure that you're in degree mode. All the interesting stuff happens when the angle is between 0 and 180. So I'm going to have to make my x range include 0 to 180. Sine never gets bigger than 1, never gets smaller than -1. So this pretty much tells me what I should use for my window settings. So I'm going to put sine of x in. Then I'm going to draw the horizontal line where y is always equal to 0.31466. I'm going to have to switch to the other calculator. This one's putting too much light out. Check your mode. I'm in radian mode now, and I want to be in degree mode. One of my graphs is going to be the sine function. So I'll put y1 equal sine of x in. My other one is going to be a horizontal straight line where y is always 0.3146601. In view of our comments about the window settings, I'm going to make x min 0 and x max 180 degrees in this case. I'm looking to intersect the graph of the sine function with some horizontal line. Sine never gets smaller than -1, never gets bigger than +1. So if I make my y range -2 to +2, that should give me a pretty good picture. So here's the sine function from 0 to 180 degrees, and you see what I'm talking about now. There's two places where the sine is going to be 0.31466. That could be angles in a triangle here. We have to figure out both of them. What we'll do is we'll use the intersection graph method like before. I'll say second trace. Intersect is number 5. I'm going to move a little bit over to the left so that I'm closer to the left end. intersection point, enter, enter, enter. And shortly comes back and tells me that X, which is the angle B that I'm looking for, is about 18.34. I've written this on the next page, so I'll just refer to it when we get there. But there's also this other intersection point here that we need to find. Second, calc, intersect. I need to be over close to the other solution, because if I'm not, it'll just lock back in on the one that we just found a minute ago. That ought to do it. Enter, enter, enter. And the other one is 161 some odd degrees. So we have figured out for the range of angles that can go in a triangle, 0 to 180 degrees, we've figured out that there are two B numbers that might work. So we have to look at two cases now. As I said, I've already written down the two possibilities for B here. The B that's about 18.34 degrees and the B that's about 161.65 degrees. In the first case, B is 18.3402 degrees. 39 plus B plus C has to be 180. If you subtract the 39 and the 18.3402 from both sides, you find out that the angle capital C is about 122.6598 degrees. Having done this, the only remaining thing we don't know is distance little c, but I'll use the version of the Law of Sines that has the distances upstairs and involves C and A. Distance C over sine C is distance A over sine A. C, the distance C, lowercase c, is little a divided by sine capital A times sine of capital C. And I know all of those numbers, so I can put them into my formula and find out the distance little c is about 26.755 degrees, that is. Case 2, if the B is the 161.6597 degree number, do the same calculation, and it turns out that angle C has to be negative to make that happen. When we measure the angles in a triangle with a protractor, we can always take the angles to be positive, so this is impossible. I can't make a triangle like that. This tells me that this second case, where the B is about 161 degrees, is incompatible with the rest of the information that's in the problem. That tells me there is no triangle that's going to go with case C, case 2 that is, C being the angle. Triangles like the one pictured, where I know an angle and I know the two sides that touch that angle's vertex, but I don't know anything else. Something like that can't be done with the law of sines as it stands, because I need to know an angle and the distance opposite that angle, and I don't know that here. There's another set of equations that we can have that's going to be called the law of cosines, and the law of cosines can handle this situation. Drawing the same generic picture as usual, we're going to have three equations, and they all look like this. One of the sides squared is the sum of the squares of the other two sides minus 2 times the product of the other two sides times the cosine of the angle, whose name is the capital letter version of the little letter version over on the left. It sounds more complicated than it is. A squared, the other two sides are B and C. A squared is B squared plus C squared minus 2 times B times C times cosine of the capital letter version of a. Likewise, b squared is a squared plus c squared minus 2 times a times c times the cosine of the capital letter version of b, and the c squared is a squared plus b squared minus 2ab cosine of capital C. These things should kind of remind you of something. Suppose that capital C was a 90-degree angle. Then cosine of C would be 0, and it wouldn't be here. And this would just say c squared equals a squared plus b squared, which we all know to be the Pythagorean theorem. So one way you can think about this is a generalization of the Pythagorean theorem, except this will work for triangles that are not necessarily right triangles. As an example of this, suppose all I know about a right triangle is that A, capital A that is 71 degrees, little b is 10, little c is 15, and that's all I know. I don't know distance little a, and I don't know either one of the other two angles. This is the kind of thing that the law of cosine works best with. So I'm going to write down one of the three versions of the law of cosines. I'm going to write down the a squared equals b squared plus c squared minus 2bc cosine a, because if you look at it, I know what b is, I know what c is, so I know what 2bc is, and I know what angle capital A is, so I know all the stuff that goes in this formula. I can literally just write it down. I typed it in on my calculator. I found out that a squared is about 227.32. I took the square root of that, the 1/2 power of 227.32, and I found out that the a to a good number of decimals is 15.07745. Now, I know capital A, and we've just figured out little a, so I can use the law of sines now if I want to get more information out of it. Sine of capital B over little b is sine of A over little a. We know this, that's no problem. We know little b, that's no problem, it's 10. What we don't know is the capital B. So multiply through by little b here. And then eventually, after you've done all the arithmetic, you find out that sine of b is about 0.6271. It's good news that that number is between -1 and +1 because there are such b's, but we've got the same issue as before. If you look at angles between 0 and 180 degrees, there's two places where the sine function takes on value 0.6271, and we need to find both of them. I won't make you suffer through it again. Get the calculator out, do the intersection of graph methods. You find out that one b that could work would be 38.836 degrees, or b equals 141.1653 degrees, also makes this equation true. It's possible that one or both of these things is incompatible with the whole scenario that we've got going. The good news, case 2 can't happen. If it did, 71 plus 141.16 plus c equals 180. Subtract the 71, subtract the 141.16, and it turns out that c has to be negative. And we said we're always going to take our angles in the triangle to be between 0 and 180 degrees. This actually makes me happy. because I don't have to worry about that case now. The other case, it would be necessary for 71 plus 38.836 plus C to be 180 degrees. Subtract the 71 and the 38.836 from both sides, and you find out that C is 70.164, which is a perfectly respectable angle for a triangle. Case 1 gives us a solution. Case 2 potentially could have given us a second solution, but it turned out not to be the case. I wanted to make a short video about this for two reasons. Firstly, this comes up sometimes in applications, so the law of sines and the law of cosines are worth knowing about. And secondly, it points out that there's kind of some difficulties in solving equations like sine of b equals 0.7, also cosine of b being negative 0.2. The solution of those kind of things is trickier than a person might think. And over the weekend, I'm going to make up a short summary of the inverse function problem for the trig functions that we know. After that, we've only got a couple more things to talk about, and we'll be done. I hope everybody has a good weekend, and I'll talk to you in the next discussion.